Alright, so rotational motion. You're going to be doing a lab where you use something similar to this, um, and I just want to sort of use this to demonstrate these three phenomena. So you can see here, there's a lot going on here. This is going to graph the motion, but just to focus your attention, here's theta, angular position, omega, angular speed, and alpha, angular acceleration. If I change this, you can see how the unit circle, this is in degrees by the way, we're going to be doing it in radians, but 0 degrees, 90 degrees, 180, 270, right? So if I move this around, you should be able to see that. So that's about 90. This should be about 180. It's not perfect, but, and then 270 down here. 360 back around, and then you keep going. You can also go negative. So that's angular position. And how fast they're going is angular speed. So if I put it up to that speed and hit play, you can see the angular position is changing because there's some angular velocity. And it's constant. There's no acceleration, so it's going around at a constant speed. If I want to make the ladybug go faster, I can do that. Alright, other direction. Yeah. So that's angular velocity, how quickly you're rotating around. And you can see actually the acceleration changes based on my change of angular velocity, but I can also set the acceleration so that the velocity changes. The graph's gone off here, but so you can see now with this acceleration, every second we're increasing by this much angular velocity, and of course our position is changing as well. So this is going to get faster and faster if I want to speed it up. Notice the direction. The velocity is always in the direction that the ladybug is headed at that moment. The acceleration is towards the center of the circle. This is actually centripetal acceleration. They're missing a component of linear acceleration, which I won't show you here. But so anyway, that's hopefully it gives you a good idea of these three. Oops. Concept 2, kinematics. Actually, in the last video, I did more explaining than I wanted to. I kind of already explained this pretty well. The only extra thing I'll do is, for example, if you have, I don't know, I'll just make up a function off the top of my head. So theta is 7t squared minus 3t. What would the angular velocity be? It's just the derivative of this. So derivative of this is 14, 2 times 7, t minus 3. And what's the angular acceleration? It's the derivative of omega. So alpha would be the derivative of this, which is just 14. So that's how you're going to handle that in the problems in the book. This is just final minus initial. You've done plenty of those. Kinematics, you've done a buttload of those so far. So I'm not going to belabor this much more, but I did want to touch upon the calculus of this. Now this one, I started talking about this and realized I was talking too much for just an introduction. So let's go into more detail here. And actually, your book has a similar sort of picture to the applet or the fizzlet I showed you with the ladybugs. So, angular distance, which is essentially how far you move around in the circle. So if the ladybug starts here and ends here, the ladybug has moved an angular distance of whatever this arc length is. You could take string, line the string along here, and straighten it out and measure it along a ruler. That's one way to do it. You could also do circumference divided by the angular displacement. That's kind of what's going on here. And so you can see that if you have a ladybug here and a ladybug here, and they both go an angular distance, let's talk in radians. So if there's 2 pi radians around a whole circle, half a circle is pi, so a quarter circle is pi over 2. So say they both go through an angle of pi over 2. That's this. That's their angular distance. Notice if they're stuck on like a solid body, like a record player, this can happen. Many objects, including like planets, like Jupiter, for example, if you look at clouds on Jupiter's surface, it's definitely not a solid. It's a gaseous, fluidy sort of material, and so things at this part of the planet won't necessarily rotate or move around the planet as at the same rate as clouds or gas material at different parts of the planet. But if you're on a solid body, this holds true. So you can see, even though they both go through the same angular displacement, the radius tells you how far they move linearly. So this ladybug definitely moves a farther distance than this ladybug. This ladybug moves the length of this line, which again, if you want to measure it, you might take some string, line it along here, and then measure the string length. You can see that the length of this line is longer than this. Same with angular velocity. The ladybug here and the ladybug here have the same angular velocity. They cover the same angular displacement in the same amount of time. In order to do that, this ladybug has to move at a higher linear speed. So this ladybug's going woo, whereas this ladybug's going woo. And finally, same with acceleration. Both of these, let's say this turntable was speeding up rotationally, starting at a slow rotational speed and then speeding up. Because they're going through the same angle, they would have the same angular acceleration. But the ladybug out here, because its radius is larger, that's the R here, it's going to have to undergo a larger linear acceleration in order to make up that extra linear speed gained. And so the ladybug will accelerate more quickly. So that's, if you want to feel less g-forces in a centrifugal sort of ride or whatever, you want to get closer to the center. And the last couple of things, in the thing I showed you earlier with Ladybug, they labeled the radial acceleration. It was pointing towards the center, but there at the end, when I added some alpha, some angular acceleration, there was tangential acceleration, but they didn't label it because of the option I clicked. But anyway, if you're moving in a circle, as you've learned earlier, that there has to be a net centripetal force. That is the net force, and so you need an acceleration going towards the center. So even if the circle is rotating at the same speed always, even if alpha is 0, then and you're rotating at a nice constant speed, then you still have something pulling you into the center, or else you're just going to want to go in a straight line. So that center pulling force leads to a center pulling acceleration. That is your centripetal acceleration. In this chapter it's known as radial acceleration. But let's say this disk starts out slowly and then speeds up, spins faster and faster and faster. You need to, one way to think of it is, in order to speed it up, you might take your hand, grab like right here, and just pull this way with a force. That force is going to speed it up. It's going to accelerate it rotationally. Notice the direction you had to pull in order to speed that up. That's tangent to the circle, and so we call this tangential acceleration. So if the ladybug is on the edge here, its velocity, its linear velocity, is going to speed up because the disk is, or the record player is spinning faster and faster, and so that you get tangential acceleration. The last thing I want to say about this is you can take those two accelerations. You can take your angular acceleration pointing towards the center. We'll call it, sorry, did I say angular? I meant radial. You can take your radial acceleration pointing towards the center, and let's say the disk is speeding up and you have a tangential acceleration tangent to the circle. The components, like these are the two components of your actual overall acceleration, which you should be able to see. This is your like actual acceleration with a tangential component and a radial component. So keep that in mind. Alright, and then let's do the third one here before I stop this video. Oops. Wait, well, that was the third. What? Oh, hey, this video's done. Do I want to? No, this is gonna take a little while. Yeah, so I'm gonna stop here.